Let's try it another way. Find me snacks for a low sugar diet with good reviews. Hello everyone, I'm Arpan Paul, applied scientist at Amazon. In this NIIT masterclass, we'll go deep into the systems that power modern semantic search, tools that go beyond keywords to truly understand user intent. Imagine launching a voice search feature on your shopping app and users say snacks for a low sugar diet with good reviews and no results appear. Because keyword search only understands words, not meanings. It doesn't know that light breakfast could mean low carb granola or that good reviews should match products with high user ratings. Hello everyone, I'm Arpan Paul, applied scientist at Amazon. Across past year, we have seen a dramatic shift. More and more users are searching with natural language queries across mobile apps, voice assistants, and AI interfaces. But here is the catch. Over 40% of the retail queries still fail due to exact keyword mismatch. In a world where users ask questions like they speak, search engines can't afford to be literal anymore. And that's exactly why you need contextual vector search. In this NIIT masterclass, we'll go deep into the systems that power modern semantic search, tools that go beyond keywords to truly understand user intent. By the end of this video, you'll be able to convert user queries and reviews into vector embeddings that represent meaning, compare static with contextual embeddings using anecdotes, store and retrieve them efficiently using FAISS, a high-performing vector index, build a retrieval-augmented generation RAG pipeline with LLMs that not only fetches relevant reviews but also synthesizes meaningful answers. Whether you are building a Q&A chatbot for your support team, redesigning a product search workflow, or crafting enterprise tools for your knowledge retrieval, semantic search is a must-have skill now. So here is the real question. What if your product search could understand intent, context, tone, or even user preference like a human would? Or what if you ask, let's say, which snack has the clean ingredients and lots of love from customers, returns an actual intelligent answer? That's what we are going to build today. Let's dive in. Imagine you walk into a store and say, I'm looking for a crunchy, low-sugar breakfast option. Now the store clerk hears your words, gets your intent, and takes you straight to the organic granola aisle section. But what if the clerk is a machine, and the best matching product review doesn't even use any of your words? That's the real challenge of search. And the solution? Embeddings. At their core, embeddings are dense vectors, long list of floating point numbers that represent the real value of text. For example, the sentence, the cereal is super light and keeps me full till lunch. This might be converted into a 384-dimensional vector. Each dimensional is like a neuron. It captures some aspect of the meaning, sweetness, healthiness, energy, texture, and so on. But unlike a tagged system, we don't manually label these dimensions. They are learned automatically through a massive training corpora. Now imagine embedding 50,000 product reviews or food reviews into a vector space. Reviews talking about sugar-free granola, low-calorie cereal start to cluster. Dessert reviews, they will float near rich, chocolate, indulgent, and so on. Coffee reviews would form another cluster surrounded by terms like bitter, strong, bold. Even if the words don't match exactly, the underlying intent does. So how do we compare them? Let's say we embed a user query, healthy cereal won't spike blood sugar levels, and we embed 1,000 product reviews. Now we ask which reviews are closest to the query in the vector space. That's where the similarity metrics come in. There are three most common similarity metrics. Let's talk about them one by one. Number one, cosine similarity. Think about each embedding as a long arrow shooting out in the high dimensional vector space. Cosine similarity looks at the angle between these arrows. If two vectors point in the same direction, they are semantically aligned. It ignores the vector length, focusing purely on the alignment. Number two, dot product. Dot product is similar, but it comes with a twist. It multiplies each dimension pair and sums them. So it provides alignment as well as magnitude. If one vector has a large magnitude and let's say it's more confident and dense because it will influence the score more. And the last one we have is Euclidean distance. This is the most common distance metrics that measures the straight line gap between two vectors. It is obviously less ideal because in a very high dimensional vector spaces, the distances tend to flatten. Most points are roughly equidistant and it becomes harder to differentiate. Think of this like Spotify's recommendation engine. You like lo-fi hip-hop music at night and you want ambient jazz while working. Spotify doesn't match just the artist name and song titles. It builds a comprehensive embedding for you and matches songs that align with your vibe, even if you have never heard of it before. Search should work the same way. We don't want exact matches, we want semantic neighbors. And the embeddings plus the right similarity metric will help you get there. Now we have seen how similarity works, let's understand how we create these vectors in the first place. From TF-IDF to BERT, we will go from static vectors to contextualized sentences. And we will about to explore evolution of how these machines need learning. Let's dive into the embedding techniques next. So now we know what embeddings are and how to compare them. But where do these embeddings actually come from? Let's zoom out and take a brief tour of how this industry has evolved from counting words to understanding meaning. Let's start with the basics. You might have used TF-IDF in college projects, right? It stands for term frequency TF and inverse document frequency IDF. It creates a sparse vector for each document with values based on how often a word appears to how important it is across the dataset. BM25 is more of a modern cousin that adds some more term saturation logic so that instead of repeating excellent 100 times, it doesn't spike the score. But both have a fatal law. They don't understand the meaning. They're just counting matching terms. Let's take an example. This snack is yummy and healthy versus, let's say, delicious and nutritious. So in the TF-IDF space, these reviews are far apart. In the vector space, they should be neighbors, right? That's why we need better techniques. So then came the first big leap for learning from context. Word2Vec by Google and Globe by Stanford. These created fixed vectors for each word by looking at how these words occur together in a large text corpora. So let's say tasty and flavorful. These might end up close, and let's say food and meal. They might be together in the near space, in the embedding space. These models help us move past pure keywords to synonym awareness. But there's a catch here. Every word has only one vector. So let's say bank loan or river bank. They will have the same embedding. So these vectors, they don't handle polysemy well. They don't have multiple meanings for the same vector. So then enters the BERT encoders from transformers. So unlike Word2Vec, BERT creates different vectors for the same word depending on its surrounding context or surrounding words. Let's say bank in bank account versus bank of the river. These are completely different vectors. Rich in rich chocolate cake versus rich in rich businessman. These will have completely different meanings. So these embeddings are context aware, a massive leap for semantic search. Elmo was an early pioneer here, but BERT brought it mainstream. Then came sentence embeddings with sentence BERT. And here where things get really useful for retrieval tasks. BERT is great, but originally it wasn't trained to compare sentences. SBERT or sentence BERT is an advancement on BERT. It fine-tunes BERT on semantic similarity tasks like paraphrase detection or question-answer matching. With SBERT, we get one fixed length vector per sentence ready to be plugged into the vector search. Best of both worlds, transformer power plus retrieval compatibility. If you don't want to load large language models locally, OpenAI offers hosted embedding models via API. There are pros like it needs zero setup and state-of-the-art performance, but there are a few trade-offs here. External API latency, ongoing cost per request, and vendor lock-in in case you are using sensitive data. Still, for teams starting out early, prioritizing accuracy, OpenAI embeddings are a way to go. So let's take two reviews from Amazon Fine Foods dataset. Review A, let's say cereal is healthy start to the day, and review B, perfect breakfast option but light and satisfying. So now TF-IDF might completely miss this match because there are no shared keywords here. Word2vec might capture some similarity, but it will flatten out on the breakfast context. But SBERT and OpenAI embeddings, which are like large language model embeddings, they will have strong alignment because these two sentences are very similar in the contextual space. Now that we understand the types of embeddings and when to use them, it's time to embed our Amazon Fine Foods dataset. Next up, we'll start with a simple TF-IDF baseline and then generate dense vectors using SBERT. Let's bring meaning to the meals. Let's get our hands dirty with the implementation of what we have learned so far. We will start with the necessary imports now. We see that we are importing the necessary libraries like the cosine similarity, the similarity metric that we spoke about, PCA for dimensional reduction, Word2vec for Word2vec, sentence transformers, as well as TF-IDF, like the embeddings model that we spoke about. Let's go to the data preparation now. We will be using the Fine Foods review dataset that we have been speaking about. You can get it downloaded from the Kaggle website, like as mentioned here. Going deep into the data, we can see there are a lot of columns, but the columns of interest that we have is the summary and the text. We have other data columns like the time, the score meaning the product review, the helpfulness, denominator, numerator, as well as the profile name. Let's start with the data cleanup. We will only retain what is the data of interest we have. We will do a basic dropping of the duplicates of summary so that we don't want duplicate vectors in our database. After dropping the columns, we see that we have a data set of around 56,000 reviews with 4 columns of interest like the product ID, score, summary of the food review, as well as the long form text which talks about the detailed review. Going ahead with the data exploration now, we will just do a simple null check. We see that we don't have any nulls in the database. Let's do a basic statistics. We see that especially for scores, we have around 29,500 summaries, unique product IDs around 67,000. And yeah, you can see the distribution of scores. Getting it like in a tabular format, we can see this is how the score review histogram looks like. As we can see, most of the scores are high scoring products, and there are very few cases where the number of reviews are less than 2. Now let's do a distribution of the text as well as summary. We can see this is how the distribution of our review text looks like as well as the summary. As we can see, the summaries are usually short form summaries which are like less than, most of them are within like size of 15 tokens, while the reviews are broader reviews where like the number of tokens or number of characters are usually around 200 to 250. Coming to the word cloud of our database, we can see word cloud is something like number of words which are most co-occurring or most occurring in the database. We can see that naturally, since it's a fine foods review data, we can see taste, flavor, water, product, delicious, sweet. These are some of the most common occurring words in the data. Now, before we go into the embedding methods, let's go back to the embedding comparison that we spoke about. So I have loaded a script which first calculates which does the implementation of TF-IDF first. We can see we are doing using a basic TF-IDF vectorizer for vectorizing our data. We will also do the implementation of Word2vec here, so this script will be available to you, and then we will do a basic implementation of SBERT. So we are moving from static to contextual embeddings like we spoke about before, and then we will do a comparative search analysis, like how the embeddings for different models look like. Let's go ahead with the implementation now. We can see we have loaded all of our models, TF-IDF, which are sparse vectors. These are 10,000 dimensions. The word2vec and the SBERT contextual embeddings are 300 and 384 dimensions respectively. Now looking at the quality of these embeddings, let's go to some hands-on examples. Let's say the query talks about terrible coffee. We can see TF-IDF naturally does not understand the context of coffee. That's why it matches with terrible, but it's actually matching with tea, which is of course a wrong document match. We can see although word2vec does rightly match to a coffee brand, but it does not understand the sentiment of what the query talks about. It talks about a coffee that is actually having a positive review. But we see as words, since these are more contextual embeddings, we can see it matches to a coffee which is having not so great review. Going to the second query, great pizza. Now again, like TF-IDF is matching to the word pizza, so it is able to match to a correct document, but like we can see, word2vec is again based on your word match, right? So it matches to something arbitrary document which has a lot of emphasis on the word great. It does not understand the contextual semantics, so hence like we can see a pizza query is getting matched to a potatoes document, which is obviously wrong. But here again we see that the match for SBERT is quite good. It matches to for the great pizza, it understands the context of like best is related to great, and it accurately matches to a pizza review, which is correct. So we can see how SBERT across various queries it's performing better than the other two simplistic models. Now let's do some anecdotal analysis here. We'll see why SBERT is performing better. Like we had mentioned before, the simple embedding models fails to capture multiple meanings or polysemy. We can see, let's say the query talks about Apple service. Apple can mean a fruit or a company, but like we can see Apple service, I would be inclined to look for services rather than fruit. But we can see the TF-IDF is matching to some apple flavored matcha tea, which is like neither apple or like neither the fruit or the company. But we can see the SBERT result here. It talks about the service, it talks about how the products and cost are great. So we can see that even though the word apple is not mentioned, it is able to capture the essence that we are talking about the Apple service rather than the fruit here. So we can see naturally SBERT understands better context. Negation handling, not bad, right? So now not bad is a counterintuitive thing, which means like it's a good enough product. So the challenge is to get the positive sentiment out. We can see TF-IDF matches something which focuses on bad, like I was able to return this item which states like bad, bad, bad. So we see that TF-IDF focuses only on the word rather than the semantics. However, SBERT captures the semantic better. Look at this review, very good. It was a Christmas gift for my father who loved it. So despite having the word bad in the query, it is able to match to the sentiment of the query, which is not bad or good enough product. So we can see SBERT captures the sentiment context better. Coming back to the third vertical, semantic similarity. Delicious, let's say take the query delicious chocolate. The challenge should be to match with something related to cocoa or chocolate. We can see the TF-IDF result. It does exact matching on delicious, like near perfect, good quality, but you can't see any chocolate mentioned anywhere. But for SBERT results, you can see it matches like chocolate, like it understands the sentiment better. Coming to contextual dependency, light coffee. Light can mean color, weight, or strength of the coffee. We can see that word2vec also matches to coffee, but it does not talk about the strength of the coffee that much. But here we can see it talks about like it's stronger than dark. So here the more focus is on the strength of the coffee. Coming to the performance analysis of these three models, of course, like SBERT are the like language models. You could see the time taken for SBERT is slightly higher compared to the simplistic models. The memory usage of SBERT is of course much higher than like TF-IDF or word2vec because these are high dimensional, bigger embedding models. So summarizing our key findings here, we saw that how SBERT has performed much better in terms of context, in terms of capturing sentiment, in terms of capturing negation, polysemy, and so on. So that is the reason, as we can see from the data set, SBERT is a much more suited candidate for our FAISS retrieval compared to the simplistic models. So, like we can see, we will go ahead with the SBERT implementation here. For the sake of latency and time, we will first sample only 50,000 reviews. I feel 50,000 is a very decent number to have a good retrieval. You'll have all types of reviews captured in that big enough sample. So let's work around with the mini LM L6. This is one of the most popular, not so large but decent enough SBERT model, which is doing quite good on the MTB benchmarks. So as you can see here, we have tried to cache this into an review embeddings pickle file, but here we are encoding the text of the model, which is the long summary, not the short summary of the food reviews, and we have encoded into an embeddings file called review embeddings. Let's just do a basic visualization using PCA. Here we can see that since all of them are food reviews, right? So all of the embeddings are clustered into a one big chunk, and all these embeddings are together. And we can expect naturally because all of these embeddings talk about food. When we cluster this or visualize this across the score, we can see that although not too apparent, but we can see the lower reviews are like clustered at the bottom, while the higher reviews are like clustered at the top left. So we can still see some sort of differentiation between how the lower review models are versus how the higher review embeddings are. So this kind of gives us a clear similar separation boundary of different product types. So far, we have turned our food reviews into embeddings using models like word2vec and SentenceBird. Each review is now a dense vector, great. But now comes the tough part. How do we search through thousands and millions of these vectors fast? Let's say you have 50,000 food reviews, each turned into a 384-dimension vector. Now let's say someone asks, find me snacks that are light, healthy, and keeps me full. You embed that query. Now what? To find relevant results, let's say you compare the query vector with each and every review into the embeddings. This is called exhaustive search. It's accurate, sure, but it's painfully slow as the data grows. To fix this, we use approximate nearest neighbor search. The trade-off with this is you give a tiny bit of precision, that's okay, but you gain massive speed and scalability. Think of it like searching your fridge. Instead of checking every shelf, you go where the fruits are grouped together. Now let's break down the main categories of ANN techniques, each suited to different types of data and search needs. The first one are the tree-based methods like KD trees, DP trees. These work well with low-dimensional spaces like let's say 50 dimensions. They partition the space into a high decision tree. But once you go into higher dimensions like our 384 dimension or 1024 dimensions, these trees get lost. It can be used for TF-IDF vectors or simple embeddings, but not for deep models like your SBERT or even OpenAI embeddings. The number two are the clustering-based techniques, like the IVF. Here's the idea. First, you cluster your vectors like k-means. Then for each search query, you search within the top clusters. This balances speed. You search fewer vectors. This balances recall. You find the right neighborhood. Think of IVF as splitting your food reviews into desserts, snacks, meals, and only checking relevant shelves. Number three is quantization-based methods. Memory is expensive, What if we could compress these vectors? Product quantization turns these long vectors into compact codes, and then we use mathematical encoding tricks. You lose some precision, right? But you get super small index sizes and fast comparison using lookup tables. Number four is graph-based. The popular one is HNSW. It is a state-of-the-art graph. It builds a graph where these vectors are connected through their nearest neighbors. So during your search, it navigates the graph like zooming in the GPS finding your location. HNSW is both fast, accurate, and scales beautifully. Think of it like Google Map for vectors. Starting far, it quickly narrows down your home in. Now you know the algorithms. Let's look into the tools. The popular one is FAISS. It's an open source, lightning fast, and it's available in C++ and Python. It's great for local prototyping. Then comes Pinecone. It's a fully managed vector database. It's good for production scale workloads. And then you have your OpenSearch. OpenSearch is again an elastic style engine with vector support plugin. Again, it is very good for production users. We will start simple with FAISS to keep things fast and transparent. We will use it to build an index flat IP index, perfect for our Find Food Reviews tab. In the next section, we'll start by building our actual FAISS index, populate it with embeddings from our food reviews, and then use it to build our powerful semantic retriever. So now let's move from theory to scalable retrieval in practice. We'll start with setting up our FAISS vector index. As we can see here, we already have the SBERT embeddings that we had previously created. We will use this library called FAISS. We will first normalize our embeddings and then index it using index flat IP. This will be creating an inner product for cosine similarity so that it's much more easier. And we will add all these embeddings to our index. So now we can see our index is created with 50,000 vectors or 50,000 Find Food reviews. Let's set up the function for searching the reviews. In this, we'll see that we'll first encode the query. And then once we get the query, we normalize the query vector and then do an index search. We will see how scalable it is. Let's look at some example queries now. Queries are, let's say, delicious chocolate, terrible chocolate, great coffee, expensive but worth it, and yummy noodles. So like we mentioned, for let's say the query one, delicious chocolate, instead of going through all the 50,000 vectors, we can see how fast the embedding retrieval is happening. So for every query, we are fetching the top 3 records or top 3 reviews. We can see the delicious chocolate, right? We can see the sentiment is the chocolate is good or the delicious. So naturally, we can see all the product ratings are quite high. 2 of them are rated 5. And when you look at the summary of the text, right, we can see everything it's talking about. Its absolute favorite chocolate or the chocolate is good. Here it wants it to be better. And it's a great dark chocolate. We can see even though it does not contain the exact words, but the sentiment is replicated. Let's come to the completely polar opposite query, which is the terrible chocolate. Now we can see that although 50% of the query is still same, it is retrieving products which have very low product rating. And naturally, since it's talking about terrible chocolate, we can see the texts that are the reviews that are fetched. It talks about like disgusted by the quality. It talks about the quality is good, but it was expecting it to be better, and it's like the worst chocolate they ever had. Now we can see that although these 2 queries are quite similar, the embedding retrieval is quite fast, as well as you are able to get relevant queries. Let's take about the third query, great coffee. Now we can see, look at this. The summary is Mocha Java. Now, although they don't explicitly talk about coffee, but we know this is a brand of flavor of coffee, so we can see the semantic retrieval in production now. We can see again it's talking about great coffee, so all the product ratings are quite high, and all the products are talking about how great the coffee is. So we are able to see that how scalable this solution is and how quickly it retrieves across the 50,000 massive vector database that we have. Now here we have expensive but worth it. So naturally you will think that since it's worth it, the product rating should be high, but the products are actually pricey. So here we see the first product price is quite high. Second is the good price for product, but just like I remembered as a kid. So here in this, it does not explicitly talk about it's worth it, but since the sentiment is reflected that okay, the product is nostalgic. And the third review, it's well worth the money. So we can see that each of these reviews have a price aspect to it as well as the quality aspect to it. And lastly, yummy noodles. Here we can see all the documents are specific to noodles as well as they have a good sentiment. To summarize, we can see all these queries, although they have like multi-context into them, like the product is good and what the product is about, we can see this retrieval is so scalable and so fast. We are getting very relevant documents. But now we can see, now the retrieval is done, right? How to make it more intelligent and more usable for the user. Next up, we have the RAG pipeline to put it into production. Imagine you are building a Q&A assistant on Amazon's Find Food reviews. A user asks which snacks are low in sugar but still satisfying according to customers. A keyword-based search might return 200 scattered queries. A vector search might narrow it down to 10 to 20 semantically relevant reviews. But the user doesn't want a list. They want a concise answer, ideally something like customers often recommend XYZ protein bars or ABC choco cookies that are low in sugar yet fulfilling snacks. That's where your RAG comes in. Retrieval-augmented generation, or RAG, is a system architecture that blends semantic search to find the right information and language models to synthesize fluent answers. You can think of RAG like your research assistant will find relevant articles and summarize them in natural language. Now let's break down into concrete visual steps. Imagine a conveyor belt, but each step enriches systems understanding. First, we ingest the corpus. Start by loading your reviews data, for instance, 50,000 Amazon food product reviews. You might store summary, review text, score, product ID for filtering. Then we do the chunking with divide and conquer. LLMs like GPT 3.5 and Claude only see a few thousand tokens at a time. So we split the reviews into chunks. Chunk size of usually 256 tokens is usually recommended with an overlap of 50 tokens. But why does the chunk size matter? Let's say if your text is too small, let's say you just chunk the word tasty, but you lose context. Tasty, but what product? Or if it is too large, multiple unrelated sentences might get chunked together with diluted relevance. Then we have embedding plus index. In this, each chunk becomes a dense vector of 384 dimensions using your embedding model like the SBERT model. You store these vectors into FAISS or Pinecone vector index. Now the system knows how to find similar ideas, not just similar words. After that, you do your retrieval to get top K chunks. At runtime, when a user asks like any reviews for low-calorie snacks that you find tasty, you embed the query, you search the vector index, you retrieve the top K relevant chunks. Now let's say 5 to 10 chunks per query. These chunks become the context for your knowledge base for your LLM generation. Finally, the generation with LLMs. Now you prompt your LLM with something like the original user question, the top K retrieve chunks, and then you might instruct your LLM like using the following reviews, summarize the best low-rated sugar snacks. Cite review snippets when appropriate. Instructing it like this might reduce hallucination and noise. Let's take an example in food reviews. If we have a query, which protein snacks gets consistent praise for taste and convenience? Here is what we got from the RAG output. Many users like Quest protein bars and Orgain protein shakes. Reviews often mention they are tasty and easy to carry. For example, perfect for travel and actually delicious. This is a summarized insight, not just a list. This is RAG in action. Let's take this theory and apply directly to our hands-on pipeline. From chunking Amazon Find Food reviews to generating real-time product insights, let's build our working RAG. For building our RAG pipeline, we will use LangChain library. LangChain is one of the popular libraries which provides great abstraction and the ease of use for LLM agentic solutions. Here, we will start with creating the document corpus for our sample data frame of 50,000 records. Now, like we have discussed before, we will use the all mini LM SBERT model. We will use a fast FAISS for our vector store like we have described before. And we will use the LangChain abstraction of all these. So now here we can see we have loaded a local vector store with our embedding model that we had previously described, and we have set up the retrieval now. Now let's just check if our retrieval is working good like before. let's say for delicious chocolate, we have seen, okay, we are getting good documents or good reviews where we have like good chocolate reviews and the ratings are high as well. So that confirms our retrieval is working fine. Now coming to the main generation code. Here we have, like you can see, we have used Sonnet 4, Anthropic Sonnet 4 as our LLM model. We have used a temperature of 0.7. It is configurable if you want like more precise or more creative queries. Like we mentioned before, this is how our prompt template looks like. We will instruct the LLM that you are analyzing customer reviews, will infuse it with the context or the chunk documents that we had spoken about, as well as we will infuse it with a user question. Now LLM will take into account the context, the question, and it has been given some instructions on how to generate the response. So this will provide us a summarized and insight instead of the raw semantic reviews. Let's go to quantitative analysis as first. Here we will see that we are like we'll look into a couple of queries. For every query, we are getting similar documents based on the similarity, and then we will see how the reviews are relevant to the query. So let's take the first example. What do people say about chocolate products? So now we can see that LLM has summarized like, okay, there was a positive feedback, there's a negative feedback. It described like what user sentiment is, what user is actually talking about, instead of looking into the raw documents. Here we can see the raw documents. So instead of getting these 3 documents, it is much easier and more insightable to get this, LLM intelligent response. We can see that our retrieval is working fine because we can see the average similarity and the maximum similarity of the documents are quite high. So we can see the query and the documents that are fetched are quite highly relevant. So this means our quantitative analysis is fruitful. Even for other queries, let's say what 2 people talk about pizza, right? So here LLM was able to summarize all the documents with preparation tips, what were the concerns, what are the positive feedback. So it is able to cluster all these reviews into a good generative insight. As we can see here as well, the average similarity and the max similarity is again quite high for all the documents. So that means the documents are quite relevant to the query. And in the last query, it talks about the complaints on users. Like we can expect, it talks about specific user complaints like the texture issues, bland flavor. So you don't have to go through the source documents, read these long summaries. It instead just gives you a summarized answer. Even here we can see the similarity is quite high to the query. Coming to our quantitative and qualitative analysis, basically we want to see, let's say, giving context of 3 documents versus context of 10 documents versus a large context of 50 documents. How will your LLM respond differently? Like you can naturally expect, like from 3 queries, 3 reviews to 10 reviews, of course the LLM will have more context to summarize. But when you go to a large review set of 50, it just becomes diluted and it just becomes irrelevant. So let's see that happen in practice. So like before, we see that we are working with 3 documents here. So here you can see that only 1 customer talked about positive feedback and 1 customer talked about negative feedback. But we can see it is not that useful for a user because, the user was asking about summary of chocolate products, but it's just summarizing 2 or 3 documents. Here we can see it has more anecdotes, like with 10 documents, it talks about various positive feedbacks as well as various negative feedbacks. So as a user, of course, I would prefer this over the previous response because I will have more anecdotes and more analysis to work on. When we take 50 queries or 50 reviews, we see that it's not adding a lot of context, but sometimes it just gets confused. Like you can see the common themes. Of course, it will add more words to the document, but from 10 you can see it's not adding a lot more value. So we can see that's the various trade-offs with increasing your context window. And naturally, if you do latency analysis, you will see in production, having a query retrieval size of 3 documents versus query retrieval of 50 versus let's say you go to 1000 documents, your latency will get impacted. So there is this trade-off between quality versus the latency that you'll have to decide in production. So now to summarize, we have successfully set up a RAG pipeline where you do proper retrieval, you do proper summarization, you do chunking in between. So we can see it's a final product to the user is just a very good intelligent insights rather than going deep into the vectors. We have come from a long way from chunking into small embeddings to getting a final good insightful output. Now that you have seen what is possible, the next move is yours. Try swapping it with a domain-specific dataset from one of your own projects. Test different embedding models, different chunk sizes. Build a hybrid search for rare and product-specific terms. You can wrap your pipeline in Streamlit or FlaskCap for internal demos. Finally, you can use OpenSearch LLMs or you can use open source vector indexes for more cost-effective deployments. Every product today, whether it's e-commerce, legal tech, customer support, or enterprise search, is being reimagined with semantic understanding. Now you have the tools to build it. The future of search isn't about matching keywords, it's about understanding meaning. And meaning lies in vectors. Thank you for joining me in this NIIT Masterclass on vector search in practice. Keep building, keep questioning, and let your search systems finally speak the language of your users. See you in the next session. Find me snacks for a low sugar diet with good reviews.